Good afternoon. Today we are going to finish talking about dynamic programming, and then we will jump into hash tables, which is a completely different topics. So, dynamic programming. We have seen already some few examples of typical dynamic programming tasks, and one of them is the longest common subsequence. So what's going on and how do we solve it? I warn you that, again, the approach is dynamic programming approach, but the overall idea is, again, a little bit different from the previous ideas. Therefore, what we've got is two sequences of some characters, of some symbols, of anything. What is important? Then they are sequences of some items. Typically we consider usual strings. And we have two of them in basic settings. Each of them has some length, and they very typically share the common alphabet, so that's just normal strings. And what's the question? The question is to pick from the first string, to pick some characters in order from left to right, and do the same in the second string. Pick some characters, not necessarily adjacent ones, in such a way that the subsequence you pick in the first and the subsequent you pick in the second string, they are exactly the same. So obviously it's possible to do in many different ways, and the example shows it. There is one example here in the middle. You've got CDA. You can pick such a subsequence, or you can pick another one, EDDA. So that's it, and the question is, find the longest possible one. How can you do it? Again, you cannot check all possible subsequences because the number of subsequences is huge. So if there is string 1, string 2, each has some length. So then the number of all subsequences is you take the length of S1 and say that, well, there it is 2 to the power of S1, and there is 2 to the power of S2 is the number of all possible subsequences. So if you want to check each subsequence, choose each subsequence from first string, and then check that subsequence against another subsequence in S2, whether the two subsequences are the same. That would result in complexity 2 to S1 plus S2, and of course that will be even omega because you still have to check the subsequences, not just pick them. So that's which is huge, and complexity. This is the complexity, of course, in the brute force approach. We have seen last time that another different problem, which was the knapsack problem, there was also the situation that we could check all possibilities, all possible fillings of the knapsacks. That number of fillings was also exponential, but we have found a dynamic programming approach which made stuff easy. So in this case, it will be a similar story in this regard, because we will go and simply apply some dynamic programming idea. What is dynamic programming idea? Dynamic programming idea says, well, suppose that you have very similar but smaller problems, and those are already solved, and try to construct your solution using the solution of the smaller problems. So the general idea is somehow hidden in this, in the next two slides, but it is very simple. So first I try to somehow decipher the slides and maybe comment on it a bit more. So what's there? Aha! So there is this case which says we have to solve the whole problem. So maybe we can use the solution of the smaller problem, namely, what if somebody already had solved the same problem with the same input, only the input did not contain the last characters in both strings. So if the same problem is solved for string A, which is indexed here by 7, just to denote the situation that in this case it is only 7 characters long, so there are, like you might think, 7 active characters, and you simply disregard the last one, and the same happens in string number 6. So now you say, okay, if we look at these two in our original problem, and we say, all right, there are two last characters are the same. Well, they are the same, so obviously you might apply the following idea. Let us take them away, so remove those 2 characters, as they have done here, and give the smaller problem to somebody to solve it. They go there and solve it and find the longest common subsequence in those mutilated strings with the end clipped off. And then you come in and say, okay, here is the solution of the smaller problem, but we know that we have removed these 2 last same characters, so now we can extend that solution, that previous solution, because there are 2 same characters, and of course that means that's another common character to the solution. So if and that will work, of course, because your person which helps you to solve the smaller problem, they find the best solution there, so it will be the longest possible one. 1 to 3 characters you cannot have any longer. So now you add the 4th character, and that's it. So if there is the best solution for the smaller problem, you can easily expand it to find a solution for your current problem, just in this case when 2 last characters are the same. So, and that's it, that's all. So we say, aha, so that again, there will be some recursive solution. Now, of course, what is immediately obvious that you can say, okay, but it's just one very special case. The last characters were the same. What if last characters are not the same? That means if you will go to solve this smaller problem, you immediately notice that the last 2 characters are not the same. So the strategy does not work, but it does not work, so you have to slightly change it, and not that much. The next slide shows that again. Shows 2 remaining possibilities. Well, if you've got a problem like they've got here, and the last 2 characters are not the same, then you don't do one thing, you do 2 things, 2 different changes to get a smaller solvable problem. First possible change is that you say, well, all right, the last two characters are not the same. So therefore, they cannot be simultaneously both part of the longest common subsequence. That can happen only in case when last two characters are the same. So they are surely not both element. They do not truly fall into the longest common subsequence. Therefore, you can say, aha, so either one of those, either the second one, which is D, one of them does not go into the longest common subsequence. Therefore, you can do the same stuff we did just a while ago. You can say, okay, let us remove intentionally just the one of those characters. Take the first string and remove the last character, and again you've got smaller problem. So let's give it to somebody who is willing to solve the smaller problem with only one string shortened by one character. And of course, because you don't know where is that longest common substring, you do absolutely the same idea with the second string. You say, all right, when we've got in another case, maybe this is not the best, but nevertheless, you will do the same, that you will submit to somebody CBDADD with E, but with the removed. So I will, just to be sure, I will redraw it here. CBEADD. E is string 1, D, E, C, D, B, D. So what you do, you do these two things, C, B, E, A, D, D, and E is forgotten. The other string is retained, D, C, D, B, D. So here is a smaller problem where somebody solves it and says, well, here is my longest common subsequence. And you do the same in the other case. So you take C, B, E, this should be E, A, D, D, E, you leave E there, but instead now you remove the last character from the second string, D, E, C, D, B, and D is not there. And now this is another problem. This problem is smaller, this problem is smaller. Those who have to solve them, they can apply absolutely the same strategy. So that happens when the end is not the end does not contain identical symbols, not same symbols. And there it is, and nothing else, in fact, has to be done. So you are in situation if you have the symbols are not the same. If you've got the same symbols, that situation is on the previous slide. You just remove all others. So let's put it there so we can see it easily. C, B, A, D, D, E, A, D, E, C, D, B, D, A. So now you do this, and those are those three cases which only can appear in any of our problems. So you go and say, haha, now of course we just, all we have to do is build a table which will somehow reflect this idea, and that example of the table is on the next slide, which now let us see what's going on. The arrangement is as follows. You take one string and put it as the use it as the row, kind of row indexes. That's I put the shorter one, and CBAD there is the other. Which one is which one does not matter. The situation is completely symmetric. Whether you consider this first string to be really the first, or whether you consider it to be the second and the second to be the first, does not matter at all. So you create this table, and then you say, okay, what do you mean? Each entry in the table, each entry in the table, not refers. It corresponds to some solution of the smaller problem. The last entry at the right bottom in the table, it corresponds to the solution of the whole original problem, which is this one. And we want to get here the information we want. And that's our standard dynamic programming table. Therefore, each entry corresponds to a problem which contains shorter strings, and how much shorter, that corresponds to the row and the column. So, for example, this blue 2 at position 5 and 4 corresponds to the first string containing only CBAEAD. So at position 5, 4, 4, this table 5, 4 corresponds to where we have CBAD, the first 5 characters from the first string, CBEAD, EAD. Second string, there are only 4 characters, DECD, DECD, and the value in that table tells us that the length of the longest common substring, length of LCS of these two strings, which are shorter than the original, has length 2. Which I hope should be quite obvious. Why is it obvious? Yes, there is E and D, E and D in both substrings. So the length is 2. How did they find out? Of course, they used the same strategy, which now there is in the table. How did they construct this particular value that the length is 2? The length is 2 because they have looked. They have looked at the end of those 2 substrings and told themselves there is D at the end. So let us look at the shorter at the shorter case. That means you remove last element from the first and from the second string. So therefore, what does it mean? That you take first 4 and first 3 characters from the strings respectively, and that is exactly the solution which is here. Which is now, that is why we have this diagonal arrow, which tells us, well, use the solution of the shorter case and add 1, because you have just added this D to the end of your solution, or to the end of your both strings. So that means this diagonal arrow means that you go here and take the number from there, increase it by 1. So it is exactly this case. In the cases which are those yellow ones, for example, take something shorter, like at position 3, 3, CBE and DEC, CBE and DEC. What you do is you say, if you want to, that's table corresponds to table 3 and 3, and then length of longest common subsequence of this 2. Again, you compute it as maximum. You take the better case. Either you take longest common of CBE and DEC, which is 1, or you can CBE and just DE. That is, in both cases, it is 1. So you take the maximum of those. When both are 1, so it does not matter which one you take. There are some other cases where it is important. For example, if you've got CBE and DCDB, for example, this 3-5 element, which says, okay, there is, if you go shorten the first character, the first string, if you want to shorten it, then you have to move to the slot immediately above it, because that means that instead of CBE, you are using just CB. So we've got CBE, and there we've got DC. CDB and DB. So if you shorten the first string, obviously the longest common subsequence has this C and B, so there is length 2. If you, on the other hand, shorten the second string, so then the longest common subsequence has length only 1. Either it is these 2 C or these 2 E's. So there is longest common subsequence length is equal to 2, and here longest common subsequence length is equal to 1. So when you go, of course, to the original to this 2, you take the better of these 2, and that is the one which corresponds to the value to which I'm pointing now. So in the table, what you do when you fill in particular slot, you look whether the characters are the same. So those are here. They are those which contain diagonal arrows. If the characters, like for example here, the characters are the same, so then you look diagonally up and take the value which is diagonally to the left up and increase it by 1. Or if the characters are not the same, like in this case, you just again look to the left and to the top and take the maximum of those. You can also look to the diagonally just to be sure, but it's not. You don't need to. So that's the whole stuff. How do you fill it? And the arrows. Finally, we arrive to the arrows. The arrows, of course, remember where did you get your optimal value from. So therefore, when we fill this table, we can fill it row by row, column by column. When we fill finally this one here at the bottom, we then just go back along the arrows, and that gives us our longest common subsequence, which is then how do you reconstruct it? Well, you move along the arrows, and anytime you meet the diagonal arrow, that means you've got the same 2 characters. Those are the characters of your longest common subsequence. So you move there. It's A at the end. Move back D. Move back. You arrive to another D. Again, move back. This last one is corresponds to E at the beginning. You can see that at the beginning you just fill these additional first or zeroth row and column by zeros, because obviously if one of your strings has 0 length, then there is no common substring. So, and that's it. We can do it. An example of dynamic programming. And the complexity. What is the complexity? Obviously, you just create this table and fill it. Therefore, the complexity is proportional to the product of the lengths of your input strings. So if they have the same length, then it is quadratic in the length of strings, and in general case we cannot do much better than that. So there it is. I hope they say it. Yeah, the code is relatively simply, as you can see. How do they do it? There is find longest common subsequence. Well, this does not generally finds it. It just constructs the table. So you go for in a range of the size of the first string, and for B in the range of the size of the second string. So it is just filling the table, and then you check whether the two characters at corresponding positions are the same. So A and B are in fact indices, they are not characters. So if they are the same, then we use the diagonally. This C is our table. This diagonally to the up left, A minus 1 and B minus 1, and increase that by 1. And remember the diagonal arrow at the same position. If they are not the same, then you go for these two possibilities. Therefore, you say, well, either you look into the you look up A minus 1, so you decrease first coordinate, or you decrease the second coordinate, one of them. So look up and look to the left from the current position and compare those numbers. So and you take the bigger of those, so that it is if the upper one is bigger, then you remember it, of course, and store this upper some value which denotes the up arrow. And otherwise, if this condition does not hold, therefore if the inequality is reversed, you store in current position in the table, you store the value which is to the left from current position, and that's it. So this is how you fill the table. And then you've got to print the solution, longest common subsequence, which of course you have to go back here, and that in this case was done recursively. Which how do you do that? At position A and B, if you are at the end, so A and B are out of the table, so there you do nothing. Otherwise, if we see the diagonal arrow, therefore we go to the left and up, and there do the same. There do the reconstruction there, and after that we print our current element, which is the first string at position A, of course, and so that we print there. And otherwise, if we are not in a slot which contains a diagonal arrow, then we either move up, or either we move to the left just by this recursive call. So it is a training in easy recursion, let us say. So this prints out the result, the longest, one of longest common subsequences. You might argue that it might easily happen that there are more than one longest common subsequences. Obviously, yes, X, A, B, Y, A, B, Z, A, B, P, A, B, R, A, B, S, A, B. If you are looking for longest common subsequences, of course, it is. This makes no sense. Excuse me, there is one longest common subsequence. A, B, therefore we have to do, so we have to do it better. Yeah, B. A, and there can be BA as well. I tried to save the day. No, that does not help. That does not help. This should help, I hope. Yeah. Longest common subsequence, where of course you take this AB, here you take AB as well. And then what do you append to those? You append either here B and B, or you append A and A. So there is A, B, B. A, or there is A, B, B. B, there are both are correct, and it will depend how you construct your table so that you get one of those. If you want to get all of those, then you have to store in each slot, you have to store, if the values in the neighboring slots are the same, then you store the same, not just a row to one of those slots, but you store there two arrows. What is then you will get a cyclic directed graph created by these by the system of these arrows. You will start here at the end, and then you will check for finding all paths in directed acyclic graph. So to find all solutions. That means find all paths in a directed acyclic graph. Let's graph, which we did not do in detail, in fact, because we did not do in detail too much directed acyclic graph. We saw them at the beginning of dynamic programming, and we can solve, in fact, a lot of questions related to directed acyclic graph. What is the longest path there? What is the size of the longest path? But if you want to find all paths, there might be quite many of them. So the number of those might be quite big, so might be quite big. You just imagine that your table contains something like this. For example, does not help. Sometimes maybe it goes from there. So what does that mean? What does that mean? That there might be you start here in the left bottom, then you move along any path which brings you finally to the top row or to the leftmost row. But as you can see, there might be too many bifurcations. So at each bifurcation, in fact, you multiply the number of your solutions more or less by 2. So that number of solutions might grow very quickly. So exponential might be exponential, so we don't present any extra method for finding all those paths. So that would be it. I hope the idea is relatively simple. Analysis is simple as well. So maybe we can at this moment finish the dynamic programming tasks. As I have told you at the very beginning, there are zillions of other similar and also dissimilar other dynamic programming problems. So we might see some others during the practices and some in more distant future. Therefore, maybe it's time to jump into hash tables, which is a different topics with different approaches, and it is, I hope, less complicated than dynamic programming. So, what's going on in hash tables? Let's see. Hash tables. The problem with the hash tables is the following one, more or less. Just a second, I want to get there. Is the following one with lots of unknown terms there. The problem is the following one. We've got, and it is a very typical one, we've got a lot of data. We want to store our data and we want to find them in our storage fast. We want to retrieve them fast. We want to be able to add fast. We want to remove them from the storage again fast, and that's all. So what we want to do is have some structure where we store data, and we want to have find operation, find our data in the storage, because with our data is associated another data which are indistinct. So that's typically, we call it a key, because we look for a key, and key is associated with some bigger data. So we'll see in the moment. We also want to insert new data, and when we don't need those data anymore, we want to delete those data, because they simply do not, we don't need them for various reasons. So you might say, okay, if you want to do this, then why don't you use a binary search tree? You can use a binary search tree. No, like binary search tree, which we have met in some detail. And in binary search tree, you know that this is O log n operation. Inserting is theta logarithm of n operation, and delete is also theta of logarithm n operation if that tree is balanced. So you need binary search tree, but not the very basic one. You need at least it should be somehow balanced. Which we have seen that we can achieve that, and now we say, all right, but in the binary search tree we have these functions which work perfectly well, and everybody might be happy with them, and logarithm is very small value compared to n, where n is of course typically the number of items we store. So what's the deal? Of course, the deal is that people want to go even faster and say, oh, no, we want to do everything here immediately, directly. No, we don't know, for looking, deciding, go to the left, go to the right, move to the next node, decide, move to the left, to the right, and go through the tree. No, we want to go faster. So we want to have this faster. And that namely means that we want to do everything in O1 time. That means in constant time. Store items anywhere and do all these operations in constant time. And you can say, okay, let us devise a hash table. And that will be the answer. There is nonetheless, if I promise that the hash table has this perfect properties, why did we talk so much about that? And why everybody talks so much about binary search? See if this is faster. So you might easily suspect that there will be some trade-off, and surely there will. So there is a small trade-off. So this is not so good. So this will be, we will cross off this. So deleting will be rather tedious, and it is not recommended to do often because it tends to be an operation. That means you have to scan the whole table to do deletion. So you say, aha, but still maybe we can survive if we do not delete that much. So okay, maybe yes. And there is another small detail which will be seen after a while, and which was not obvious in binary search tree. But binary search tree is flexible in that technical sense that when you are inserting and inserting and inserting, there are virtually no limits except for the architecture of your machine. So the limit is just so-called. The limit is limit is hardware limitation of your binary tree, because you need just enough memory and just enough addressing space to store new nodes of the tree, and there it is. The problem with the hash table is that it is a table. Has fixed size. And when it has a fixed size, so you go and you insert in your table, and suddenly your table is full, and you want to insert something new. So in that situation, you say, but our table has fixed size. What now? Then you have to when you have to add something more. So if it overflows, you have to create a new hash table where you store everything. All, of course, create bigger table, and so-called rehash values, keys or entries, all entries, all entries, which means take them from the old table, put them into new, bigger table where they can live happily with all new other keys which has to be stored there. So, so those are just some minuses. Number one is that deleting is not so nice. It's not nice at all, as we will see. But there is this. So if your table is too small and you have to make it bigger, that takes time. But all the other two are fine. How does that is achieved? Let's have a trivial example for the beginning, and from that example it should be more or less obvious what's going on. Only we will have to do some tweaks, some small changes, just to make the idea work nicely in nearly all cases. So let us have some few keys. And I will use some numbers, some integer numbers: 43, 17, 21, 32. Is the 4? Let's take 6 of them. I cannot think about any other number. I completely out of my 25 and 10 maybe. 2, 4, 6. So let's in reality there will be not 6 items, but 6 million. Doesn't matter. Let's say we have to store them. If I asked you to store this in a binary search tree, you will not hesitate how to do it. But now we will do a different stuff. Let's store it in a table. So in a table. So we've got these 6 values, and we want to be able to insert new values and to find them quickly in our table. So what will you do? You say, oh, that's no problem. You will create a table which size is from, I don't know, from 0 to 50, for example, and at position 10 you will put key with or reference to data which are related to 10, and all at other positions like 11 or 12 you will put a null or none or nil reference. So anytime you are looking for 10, you just jump into your table. Very trivial. Everybody can think about such solution. At position 17, again at position 17 there will be your reference to data which are connected to value 17 and so forth. At position 25, 21, 25, 43 there will be. So the obvious problem is that when you don't have that much space, or when your keys are big, you can imagine that those are in fact something like this: 21. 32. So if you want to do the same stuff with the following values, then of course this strategy makes no sense, because your table would then start somewhere at 17 at the beginning, at 0, and then you will need 200,000 entries, or you can imagine a few more zeros there. You will need terabytes of data just to store your six values. So that's not always a good idea. So to help you say, aha, but that might not. Let's say that don't look at it as a big value, somehow make it smaller. How you can make it smaller? Modulo. Take it modulo some small number, and that number will be in fact the size of the table. So what you do, you say, okay, instead of my keys, be they small or be they big, does not matter, I will reduce mentally my keys to smaller values. So take values, take keys, for example, modulo a table size. So there are 2, 4, 6 keys, so I am going to create a table which 0, 1, 2, 3, 4, 5, 6, which size will be just exactly 7, and take all these keys modulo 7. Modulo 7, and therefore the remaining after division by 7, and then store that particular key at the position which is not the value of the key, but the value of key when it is reduced. So 43, what is 43? 43 is 6 times 7, 42 plus 1. So you say, that's position 1. 17 is 2 times 7 plus 3. So you say, remainder is 3, so we will put it at position 3. 21 modulo 7 is exactly 0 because it's 3 times 21 is 3 times 7. 32, that's quite difficult. That's 4 because 28 plus 4 is 32. 25 is 21 plus 4. So there it is. And 10 is 3. Now it turns out that it was a really bad idea to devise such strategy because now you say, okay, so you can take 43 and store it there. So anybody who asks you, is there 43 in your data? You say, okay, 43, compute the remainder, that's easy, that's 1. Look at position 1 and say, yes, it is there. If they ask you, is there, for example, 44 in your data? You say 44 modulo 7 is 2. Look at position 2, there's nothing. No, we don't have 42. 44, and so on. So 17 goes at position 3, 21 goes to position 0, 32 goes to position 4, and now what happens to 25? And now the obvious drawback of the whole idea is here. 25, you want to put 25 there, but you've got a problem. So it does not work. If we had not this problem, if we had not this collision, so it's a so-called collision, if we had not this collision, in fact there are 2 collisions as you can see, the problem would be solved. So if we had only these data, not these annoying ones, the problem would be nicely solved, and we will be happy with small table where we store everything and we can easily find in constant time, and if provided there is a free space, if you want to add 44, now it is again possible in constant time, and you can find there in constant time those values. But that, of course, now has its problems, but we are here to somehow solve those problems. Then we have to fix the problem. So we have met the thing which is called a collision. And most of topics related to hash tables are related to collision solving. So we have collisions, but also we have their collision solving strategies. So we will not be deterred by this fact that we have collisions. We will instead solve them. How do we solve them? Well, there are, as you can see, what they promise us on the slide. That they say that they will do something, resolve collision by some methods. Nice. And first they talk about hash function as well. Hash function. Where is the hash function? The hash function is the function which takes the original key and translates that key into the position. So in this case, our hash function, which I can put down here, hash function, our hash function, it takes a key and assigns to key its position in the table. And in particular, here what? That's an example. What we have done, we took a key, k like k, key like k, and what do we said? Take k modulo 7 or k modulo table size. You don't have to do, as we will see next time, you don't even have to take each time modulo size, but nevertheless we've got that. So k, take k, which is some let's say big value. Now you can see that it does not matter how big that value is. If you can from top of your head, which I cannot calculate this the value of this key modulo 7, then you will get its position. So we've got this, and now we have to solve the collision. Now the answer to the collision, if we want to finish the job, is simple. Put the colliding value, we put new colliding value somewhere else. That's it, nothing else. Put colliding value elsewhere. Put the colliding, the colliding value elsewhere. Even you can do it outside the table. So I'm going to show you now a few elementary ideas. What can we do? They are listed out there. So you might think, okay, if it is colliding, you may create some additional bag which is absolutely unstructured, and you can put it there into your bag, where you can say, well, if it is colliding, just put it inside, and if somebody comes and asks us for 25, then we will compute where should it be. It should be at position 4. Look at position 4, there is somebody else. So if that 25, if we register it, it has to be in the bag. So then you go and check the bag. Is that 25? Either yes, either no. But that, of course, is not very nice because again, there is no structure in the bag. So now you can say, well, how do we have to put some structure on this bag also to be able to find it there. And typically, of course, it should be also simple to implement the whole stuff. So if there has to be some structure, you can say, okay, let's have a list. So what you can do is you say, okay, let's append a list of other keys to a particular slot in the table. So anytime somebody asks us, is there 25 in your table, we apply a hash function, get position 4 out of 25, go to position 4, and if it is not in that slot 25, then we search the the list which is attached to that slot, looking for that value. For example, if they ask you now to insert another value, which just to get a remainder of 4 should be, I can't imagine, 39. That also has to go to position 4. You will create simply append another 39, append another value there. So there is this, there might be this list of what? List of synonyms. Synonyms. What are synonyms? Synonyms are the keys which want to sit at the same position in the hash table. So synonyms are the keys which the hash function assigns the same position in the table. Therefore, they are colliding because they want to sit at the same position. The same position in the table. In the table. So you've got list of synonyms at each particular position. As you can see, if you want to add 10, which has to be which is mapped by the hash function to position 3. At position 3, there is already 17. So you create a list there where you store your value 10, and that it is. It might look strange a bit. You say, aha, and what if we are unhappy, or sorry, if we are unlucky and therefore unhappy after a while, if we are unlucky and the values which are the keys which we have to store, just by chance they are mapped to the same position. Then you say, aha, and if we got such kind of keys that they will be mapped at the same position, then the whole table will be empty. Only one position will be occupied by all the values, and the whole sense of the hash table simply is totally destroyed because it's simply meaningless. There will be just one list of values. So there is another not a problem but a property of hash table. There is a distant risk of too many collisions. And how to reduce that risk? Standard answer to that is create a good hash function. So that should be more or less something like unpredictable what that hash function does. In that sense that when the keys are coming in, so the hash function, just if it is this fixed, well, then it simply does not fall into that problem. So typically you cannot solve it in advance. So you try to go for such hash functions which you say, okay, if you modulate it by, I don't know, by 107, that's nonsense, 19, by something like that, it is very highly improbable that if you take not just modulo 7 but modulo some bigger prime, let's say, then of course it is very, very unlikely that we will have too many values to be of the same remainder after division by that value, and therefore you can assign very low probability to the event that there will be too many collisions. So that's the standard answer to this problem. Now, okay, but that's rather somehow simplistic. So let's just see the other possibility, which says this is a little bit problematic, this approach. That's a collision resolving strategy. Well, all right, but when you go implementing it, the obvious problem is that you have to create these lists in your machine. You have to allocate, each time you have to allocate some additional space inside your machine. Therefore, of course, it will again take some time, some extra additional space. Maybe your programming language takes a lot of time to manage a single list, which is more or less typical with today's programming languages. So maybe not. Maybe you might not be quite happy with this setting. You want to keep one table, and then you go for the second case, which is mentioned there, so-called open addressing. Collision solving strategy, put the colliding value elsewhere. That is what we have seen. You can put it outside the table, or, of course, inside the table, but simply elsewhere. Well, where? At first free position. So if you've got the same value, so I will draw another table here of the same size for the same keys. So 0, 1, 2, 3, 4, 5, 6. There is our table where we are going to store our values, and 43 goes there, 70 goes there, 21 goes there, 32 goes there, and now 25 wants to go to position 4. So what you do now, you say, all right, we can 32. So when that position is full, move forward in the table and use the first free slot you will find and store your 25 there. When you do this, you say, aha, but now can we find 25 later in our table? Because now we depend on our hash function. When anybody is interested in key 25, hash function tells us that it should sit at position 4, and it is not sitting at position 4. But the strategy which says put it into the table inside, that strategy works, of course, not just for inserting, but for finding as well. You say, aha, we look at position 4. If it is empty, then we know that 25 is not in our table. Because you can see, when they ask you for 44, you look here at position 2 and you say, hi, that's empty. No, we have no 44 in our table. When they ask you for 25, you go at that particular position, and now you see, well, there is something. There is 32, which is not 25. Therefore, if there is 25 in our table, it must be somewhere else. And the strategy is go searching for in the next, you go searching for it in the next slots, and you go searching for it until you either find it, either find some next free slot. So now you go search, look for it, 25, it is there, it is there. If you want to look, for example, now as I have said before, so 35, they ask you find 39. What you do is you say, hash function of 39 equals to 39 modulo 7, which equals to 4. So you go with 39 to this position. No, that's full. There is 32. It's not 39. So move forward. What's next? There is sitting 25. All right. So search again on the next in the next slot. Is there 39? No, now we have found an empty slot. So now we know that it did not happen. It did not happen before that we had put 39 there. So it is not find in the sense that it is not in the table. Not that we were too clumsy to find it. No, they're not found. Not found, so not in the table. Not in the table. Not in the table. So, so the solution is there. You say, instead of creating these lists outside the table, you are in fact creating them inside the table. And that's it. Now again, if you want to be careful, you say, yeah, but now what? Now you can see that there are some kind of disadvantage in this approach, which says, okay, and what if we are looking for 38, for example? Find 38. Find 38. It's easy. You say, I have my hash table, hash function of 38 equals, I computed it directly, probably it is 3. So go look at position 3 into your hash table. And now you can see that although 38 is not in the hash table, we discover it only after examining that slot which corresponds to the value of the hash function, okay, but there is some other value sitting in there. And then we know that it might have happened sometimes before that we that we inserted 38. So we have to look into the next slots until we either find 38, either we find an empty slot. But of course, what is now the disadvantage that we do not check all the just the values or just the keys which were colliding with 17. We also, because we look into other slots, we also check the keys which were colliding with 32 and 25, which is a totally different value of a hash function, which means that we are going through again through bigger chunk of the hash table. So looking for the key might involve, right, as it is in this case, might involve probably involve checking the synonyms of other keys as well. Why? Because of course they are just neighboring in the table. So those synonyms of other keys which we have to look for make it more difficult, and we have to somehow again solve this thing. Those are so-called clusters. Clusters are continuous parts of the table which are filled with stuff. So any time you search for something and you don't find it immediately, you have to go through the whole cluster. So the cluster is these synonyms of other, which let's say we will call clusters. Clusters, and what you want to do ideally is, when you have got, there are two examples of hash tables, and let's say the number of the key, there are the same keys in both hash tables, but they are of course using the different hash function. Same keys, and now imagine that the first table looks something like this, where of course the highlighted area are the only areas with which contains the keys. So those are clusters of keys. They look like this. And you have the other table where the situation is like that. Yeah. So they are the keys are in different arrangement, and this is low clustering, and this is high clustering. Just because whenever you are looking for something, you are sure that if you are going through the cluster, that cluster is always short. So low clustering, that means short clusters. Short cluster. So you are quite sure that anyway, anytime you look for something, you go through the cluster, but that cluster is short. After a while, you come to a free space and you say, aha, if I am looking for something, I have not found it, or if I have found it, but it is at the end of the cluster, so you still have to go through the whole cluster. The high clustering, of course, they are long clusters, because imagine that you want to look for something there at the beginning of the cluster, then you want to go and find that value, and if you don't find it immediately, you have to check the whole cluster until you either find it, either confirm that it is not in your table. So therefore, of course, this is more desirable. The left one, the right one is not that desirable, and that means that the hash function, one property of the hash function should be that it disperses the input keys more or less nicely through the whole across the whole table. It does not support. It does not concentrate on one part or another. So it is more or less regularly disperses the value. So it is desirable. So disperse the keys, not regularly, but uniformly in the table, in a uniform manner, which is a desirable trait of the function. So for example, we'll see maybe some additional examples. Okay, so now, now you might, and now what we will do is we will try to be more and more clever in collision resolving strategies. So far we have seen basic approach, which as we see has some dangers in it. You say, aha, and maybe it happens that there will be long clusters, and of course that will slow down significantly all operations, so it is not good. So let's do the better approaches. First of all, you can say, aha, so if what's to do to go for this better left picture, you say, well, whenever we meet a collision, we might say that we will not use the next, we will not search the table just one by one. Let's make bigger jumps. So it will be still so-called linear probing, but you will say, okay, if after collisions move by some number of slots forward, not just by one. So you say there inside in linear probing probing after collision move forward by one, which is not very good, or by more, or by a constantly more, that's nonsense, by one, or by constant number of slots. That means, for example, when we are still in our introductory situation, we've managed to insert first for keys, because that's not difficult. After inserting, so now insert 25, and say after collision move by three elements. So we might say that key, the hash function, assigns to the key, let's say to the key, assigns key k modulo 7, and then it just does this. I will write it in some plus I times 3, and again that whole stuff will be modulated by 7, which is too long. Typically you say k plus I modulo 7, it's the same, 8 times 3, sorry, 8 times 3 modulo 7, that's the same. That's the same, and I is the number of collision. I is the number of collisions, because as you move forward, you meet another through the cluster. When you have collision, you move to the next slot, and again it is full, so it is again a collision. So the number of collisions is given by this index I, and when there is no collision, then I is 0, and you've got your original hash function. So what you do now is to say, aha, 25 comes in, we've got a collision, so the hash function tells you that originally it has in step 0, we had 25 modulo 7, which is 4. Now there is a collision, so we take 25 plus 3, move forward by 3. 25 plus 3 is 29. 29 modulo 7, it is 28. Sorry, excuse me. So 28, 25 plus 3, let's write it this way. Modulo 7 is now 0. I hope. So you say, aha, we don't put it there. We go 1, 2, 3 slots forward. Is there a collision? Unfortunately, there is a collision. So we say, okay, 25 plus 6 modulo 7. 25 plus 6 is 31, modulo 7 is 3. Which is 3. Is there a free space? No, it is not, because it is occupied by something else. So we've got another collision. So now you say, okay, 25 plus 9 is 34, which is 6 modulo 7, which is 6, and finally your 25 might sit there. So this was an example which at first sight looks a little bit more, but maybe it is good. It looks in fact not good, because you say, well, we tried to devise a better strategy and we end up generating a shipload of collisions. No, that doesn't matter. We might still improve the idea. First of all, let's say this was just an unfortunate case. Try to insert now this value 10, which has to be sitting at position 3. So now if we have to sit at position 3, then 10 will collide here. 1, 2, 3. It will collide with 25. 1, 2, 3. It will go into position 2. But as you can see for the future, the table already has a little bit structure like this one on the left, that there are short clusters, but who knows how they behave when we make longer jumps. So the other improvement, which is named double hashing, will do the following. Double hashing. Hashing will do the following. It will say, so far, what we are doing so far is that we treat each key which comes in and which we want to store in our hash table exactly the same way. And now we create that additional strategy, which will say, okay, all keys which collide, all synonyms which collide on some position, fine, let they collide, but for collisions on different places, let us have different shift. So synonyms, different synonyms. What are we trying is to disperse the values as much as possible across the table. Different synonyms. No, names will have different, if possible, different shift after collision. Shift after collision. So you might say, okay, let's do the following and continue the example. Which says, after collision take K and assign to it K modulo 7. And if we have a collision, then we will take another hash function. That is why it's called a double hashing, and modulate it by different value. Like, for example, a 4 in this case, and multiply that by I. Then modulate everything by 7 to fit it, of course, into the table. So again, you can do it You can somehow simplify this formula, but that does not matter. What do we want to do is, in the last 2 minutes we have, is to do again the same stuff. 0, 1, 2, 3, 4, 5, 6. Store there this 21, 43, 17, 32, and then look what happens when we try to insert 25. When we insert 25, I is 0 because there was no collision yet. So we again 25 as before with no change is trying to get there. Now it cannot be there, so you can say okay. So take 25. Probably plus 1 is there important. Excuse me. Does not matter. You can think it's just some function, some additional function which more or less should behave if we are lucky, should behave unpredictably. So if it behaves unpredictably, then use it and say, okay, 25 goes to position 4. Now that position is occupied, so you can you say, well, we will take position 4 and add to it k, that's key modulo 4, that is 1. I hope 25 modulo 4 is 1. It is multiplied by 1 because we had 1 collision and added 1. And that means that 25 will go to this place. Okay, so now it is there, no collision, fine. Try to insert last value 10. 10. So if we are inserting 10, 10 wants to go to position 3. So the key is 25, and now when key is 10, what we want to calculate, 10 modulo 7 is 3. Now we add this stuff. We take the key modulo 4, which is 2, 1 plus 2, and we end up the same place, haha. So there is this, this is 1 plus k modulo 4, so this is what times 1, I think, because this is 2, this is 1. So we end up at position 6, which is already occupied, but now we have a different length of the step. This is the length of the step is 3. Step length is 3, I hope, or no, is 2. Is 2, I hope. 2, yeah, I am right, no. Because their step length was 1, does not matter. Inserting k, taking 10 is 2, yeah, so that is 2, and we add each time 1. So we have now 2. So we have 4 plus 1 is 5. So we take 3 plus 5, which is 1, and again we end up in a different place, and then we have to do it even more times. So the example showed us that it's not that easy. So we will finish these topics next time. What we have seen so far is that we have the hash function. Hash function tells each element where to go and where to look at it. After collision, we can apply a few different strategies, which, as you can see on small examples, sometimes look nice, sometimes look bad, but the examples are so small that it is hard to derive any obvious conclusion. So the conclusions we will derive next time, what is good and what is not good. And the idea just says there are more ways, and in fact you might come up with many different ideas of collision resolving, and people have done so, and next time we will see more ideas how to resolve the collisions. So all that remains is to see how it behaves in real life, which we will do next time. So thank you at the moment, and see you on the practices.